Hello, my name is Oren Wallace. I will be presenting the paper Do You Hear What I Hear? Fingerprinting Smart Devices Through Embedded Acoustic Components. The presentation is part of the Intro to Cyber Physical Security class, CS 62263. This presentation is happening on November 3rd, 2019. Some acknowledgements for the paper are the original authors, obviously. We have Anupam Das, Nikita Borisov, and Matthew Caesar, all three of which are from the University of Illinois, and I have provided a link to the paper as well. Smartphone usage has greatly increased over the past decade. As such, ownership. Proliferation has penetrated nearly every corner of the market, and these days no one really can go without their phone. A novel idea that the authors observed was that manufacturing imperfections exist in all manufacturing processes. Thus, the process for creating phones must exhibit some imperfections and idiosyncrasies. From these imperfections, we can actually fingerprint a specific device within a known set of the same devices using either a speaker, microphone, or combination of the two. Some research that the authors performed for the following paper was they assessed the feasibility of fingerprinting, specifically using microphones and speakers. They used a large set of audio features to fingerprint with. One observation that they noticed was Mel frequency cepstral coefficients, or MFCC, perform particularly well in fingerprinting. The authors employed two separate classification algorithms to classify audio clips. One utilizes a k-nearest neighbor method, and the other uses a Gaussian mixture model. Various audio clips were used in the testing process. They range from simple sounds to human dialogue. And the authors considered some factors when fingerprinting devices, such as sampling frequency, training set, ambient noise, distance between the speaker and the recorder. Some related work in the field the authors listed as examples of differentiating devices not pertaining to speakers or microphones. Some of them include mainly network analysis of devices, 802.11 probe requests, observing trends in wireless traffic, and anyone can use tools such as Nmap or Xprobe to fingerprint or identify devices over a network given list of open ports and available applications. The authors presented a specific paper which detailed a W.B. Clarkson who showed that distinguishing loudspeakers is possible through various methods. One thing that was interesting was that he only achieved an 81% accuracy in discerning loudspeakers from audio clips. He used audio clips which have 65 different frequencies, and there's not really much of those in the wild. You're not going to be able to record those and actually fingerprint something. And interestingly enough, the Clarkson found that there was no variation among microphones. These authors show otherwise. Some other notable research in the field includes classification based on content, determining human speakers based on audio recording, and songing artist recognition applications such as Shazam and other things like that. So in order to create a fingerprint, we have to have some sort of device which exhibits differences and we can actually evaluate those differences. Let's talk about microphones first. Microphones embedded in smartphones these days are almost always microelectric mechanical systems, or MEMS. And typically there's multiple of them. iPhones have one for canceling noise, one for listening, and then one for attempting to block out additional filters. In this figure, you can see we have a simple version of a microphone. The black bar there is this diaphragm, which moves back and forth given some sort of air pressure changes caused by sound, which propagate through acoustic holes. From the movement of the diaphragm, we record an electrical signal and then can translate that into sound. Some of the sensitivity of the microphone often depends on the amount that the diaphragm can move or how flexible it is, the deflection. Some interesting important things about fingerprinting microphones is the inconsistencies arise from chemical composition changes in just chemicals applied to the structure of it. Manufacturing machines wear and tear causes small differences in the construction, and temperature and humidity have an effect on the creation of microphones. Another source of fingerprints is speakers that the author has attempted to derive from. Micro speakers are within all phones these days. Another example of MEMS architecture. Sound is produced by creating a current that moves a coil up and down and causes the diaphragm to move and displace air. The diaphragm is held in place by suspension, and there's a backplate or a basket which holds the diaphragm in place. Varying the electromagnetic field around the coil allows different rates of oscillation, vibration for the coil, which allows us to create different sounds. B is a picture of a small speaker found within a phone, and C, you can see it has the same structure, same components, and they're just minified essentially. Same as the microphones, we have similar inconsistencies, chemical inconsistencies, temperature, wear and tear of machines manufacturing them, and speakers can also have electromagnetic property changes that cause a diaphragm to move at different rates. So, thus, no two speakers. The authors considered 15 unique audio features when attempting to fingerprint smart devices. All 15 can be seen in the table in the paper, table 1. From the 15, they attempted to find a reduced set which provided the highest classification accuracy. We'll go into how they did that. They did it a few different ways. And notably, the Mel frequency cepstrum was the most influential audio frequency observed. And the cepstrum essentially is the representation of a short-term power spectrum of sound, and it's based off of a linear cosine transformation of a log power spectrum on a nonlinear Mel scale of frequency. And they look at MFCCs, which is the last C is coefficients, and essentially there's multiple cepstrums that they use to match a fingerprint with. So the two classification algorithms that were employed by the authors are a k-nearest neighbor algorithm, which is a non-parametric lazy learning algorithm. The non-parametric essentially means that no assumptions are made about the underlying data, and that's something the authors were very particular about because they don't want new data to be created. They want the data to be assumptionless. And the k-nearest neighbor algorithm uses training data given to it in an attempt to learn data points. Again, the authors chose this because no generalizations were made So the given data is going to match what we know, not a new generalized set of it. The other classification algorithm that was utilized, and which actually turned out to be the better one, was a Gaussian mixture model. And this is a probabilistic model. Data is generated from Gaussian distributions that they have unknown parameters. These types of classification algorithms are actually often used for biometrics, and they're useful because they actually can represent a very large class of a sample of distributions. The authors attempted to fingerprint devices in a realistic setting. They utilized a office building that was given them from their university. It contained normal stuff in it, desk chairs. There was an open hall to there was an opening to a public hall, and it received a decent amount of ambient noise thanks to air conditioning, fluorescent lights, stuff like that. They placed smartphones throughout the vicinity in an attempt to emulate victims, and for their main attempt at recording and fingerprinting devices, they used a laptop situated somewhere within the room to simulate the attacker. This was an Acer laptop. We can see from these two tables the devices used. We had 52 different devices. There's a range of different types of phones here. Apple, Google, Samsung are the makers. Different types of models. So decent sample size. And they also showed the type of audio clips that were played. There's instrumental, human speech, and song, and we had different variations of those. Some of the programs used were MRI Toolbox, MIR Toolbox, NetLab, Audacity, and Hertz. The authors used some basic multi-class metrics to assess the applicability of fingerprinting devices. They went with precision, recall, and F1 score. You can see in the equation 1, TP is the true positive rate that the classification algorithm yielded, so ones they got right, and FP is the false positive rate. So precision is computed like that. Recall is something similar where we use the true positive over the false negative to see which ones we actually got right correctly. And then the F1 score, which is used throughout the paper, is a combination of them, which kind of gets a generalized average of it. And then they go into using the average of them, which is just the sum of our observed PRs and precisions, recalls, and F1s. The audio clips were, for sample size and recording purposes, they play them 10 times, and 5 times were used to create training data for the K nearest neighbor algorithm, and then they used 5 times to actually test them. The authors describe 3 different methods for fingerprinting acoustic components. The 3 pertain to fingerprinting with speakers, microphone, and a combination of the 2. For speakers, the main problem that an attacker needs to overcome is recording your cell phone, essentially a ringtone or something, which is not too difficult to do. We see the general flow of things like so in figure 3. Essentially, a smartphone creates a sound. We record that on a laptop, PC, some sort of microphone. We analyze the acoustic features. From those, we extract them and generate a fingerprint, and later we then can match that fingerprint after we hear it. Fingerprinting in microphones is done similarly. The attacker essentially needs to obtain a recording of the microphone, and then they extract the features, generate the fingerprint. The attacker would need to essentially install an application or on the phone of the smartphone in order to do this. A little more difficult. And finally, the integration of speaker and microphone. Essentially, it creates a sound that then it records and you use that to extract the features from and generate the fingerprint. This would really likely only be a game or some sort of application that has access to both components. And lots of things these days do request both applications, but or both permissions for speakers and microphones. So it's not unlikely. The authors present a feature exploration algorithm for determining the dominant subset of features for a fingerprint. One would think, why not use all audio features shown, essentially all 15 of them? And what can happen is essentially performance degrades as we add more and more checks to our algorithm. So we want to find the best set that gives us the best answers. The authors developed an algorithm for selecting it like so. We start with a set of f-scores where we use one feature alone to classify with. So we have an array of f1 scores. From that, we sort it in descending order. So we start from largest and we loop through each element, unioning, and then using that new list to classify it and seeing if we come up with the greater score. If we do come out with the larger score, then we keep it, else we skip that feature and we move on. This is a greedy algorithm, so it will actually not compute the optimal set, just the best set that we can see at the time. The authors chose to use feature selection as opposed to feature extraction, and these are both machine learning algorithms. And now we'll go over some of the results the authors presented using their various tables. They start with attempting to fingerprint devices of different maker and models. So we started with 5 different vendors. They range from Apple, Google, etc. And for those 5, we have 7 different smartphones across the 5 vendors. Table 5 shows fingerprinting using just speakers, and we give results. The authors give us results for the KNN and GMM classification algorithms. We can see the average precision, recall, and F1 scores of them, and GMM clearly outweighs K nearest neighbor in this case. Similarly, below, table 6 shows the results using a microphone. As above, the GMM actually performed better, and so we're probably going to tend to see that trend as time goes on. Table 7 shows the combination of using both a microphone and speaker, and these will always be greater than the previous two because we take the best of both answers, essentially. The authors present data and results from the same make and model devices, which actually turned out to be a tougher problem, according to them. They utilized 15 of the same devices, Motorola Droids, and we can see results are actually somewhat lower than previously. KNN produced precisions around 93, 96. Average F1 scores were in the 92s, 96. And again, GMM performed a little better than K nearest neighbor in nearly all regards. As we can see in table 11 there, we have 100% fingerprint recognition using smartphones, microphone, and speakers for same make and model. The feature selection algorithm essentially came up with the fact, or revealed to the authors, that MFCCs are by far the best way to classify a fingerprint. As I stated before, there are a collection of coefficients which make up a specific MFC. These are 3 different bar graphs which have 13 different coefficients laid out from 1 to 13. And these are actually coefficients from 3 of the same phone types. sorry, same vendor and 3 different phones. So 3 iPhone 5s essentially, or something like that. The frequency bands we can see are they're equally spaced on the Mel scale, and the Mel scale is an approximation of the human auditory system. And looking at the bars, we can see that there's very different peaks and lows between these coefficients. So they're very useful for fingerprinting specific devices. The authors present near the end of their paper a combination of all devices, all 50 essentially, they attempted to fingerprint. And at this point, they used the speaker and microphone results just to get the best results. And we can see in table 12, uh, we had our respective uh, fingerprinting score and each feature for the different audio types and our F1 score. MFCCs at um, row 13 score clearly higher than everyone else. Close second is Cro-Magnon, and then tonal centroid. Fingerprinting all smartphones using mics and speakers is shown in table 13, and we achieved essentially 99% accuracy in almost all regards. Finally, the authors took into account a sensitivity analysis when attempting to fingerprint devices, and they looked at 4 separate criteria: audio sampling rate, the training set size, distance, and background noise. One thing that they considered is we only consider fingerprinting similar model smartphones, since this was a harder problem, and they were only using speakers to record fingerprints, thus simulating an attacker more exactly. And also, they only used audio clips to record. Like, yeah. Audio sampling rate was considered first by the authors. They used rates of 8 kilohertz, 22.05, and 44.1. We can see by figure 7 that as sampling frequency increases, the average precision and recall of a fingerprint increases, unsurprisingly. Notably, nearly all phones these days have a 44.1 kilohertz um, speaker to sample at. The training size, which was used for the k nearest neighbor algorithm, is used to train the model, and having a higher number of training size can slow results, and a lower number can provide inaccurate results. We can see that after a size of only 3, we achieve an F1 score that's greater than 90, so it's pretty good. The authors took into account the distance between the speaker and recorder. To do this, they actually used a Audio-Technica microphone because they noticed that laptop microphones degrade drastically as you separate them. Some of the results are in table 15. We can see that after about a distance of 3 or 4 meters, we really start to lose accuracy for fingerprinting. But at 2 meters, we actually can sample at about, or we can fingerprint at 93%, which is somewhat scary. They also considered ambient background noise because if an attacker would be performing such a recording, there's likely to be lots of ambient noise. They did this by creating multiple sound sources around the speaker and recorder devices they used. 2 meters from source up to 2 meters, and we can see the signal to noise ratio was from 15 to 18 decibels, and we still achieved near 90% accuracy for every case. Some limitations that the authors noted were we only took into account 25 different devices. Having more might actually have lowered the accuracy, but having this many devices allowed them to create distinct boundaries between device types, which was useful. All of their experiments took place in a lab setting, so that could have affected ambient noise and randomness that could happen, but they did take into account several factors in their sensitivity analysis. And finally, no phones were actually in mint condition. There had been wear and tear inflicted on them, and clearly that was shown in some of the fingerprints. But this is actually likely to occur in the real world, and it might actually create more notable fingerprints for devices. So in conclusion, the authors have shown that it is definitely feasible to fingerprint smart devices using speakers, microphones, and a combination of the two. They've shown that fingerprinting can potentially be a privacy concern. Fingerprinting is possible in controlled environments and in the presence of ambient noise, loud ambient noise, and it's really a major step in understanding the possibilities that fingerprinting can achieve through acoustic channels. And thank you for your time. I had a good time understanding this paper.